It's called ThinkAsync in Java8. A few words about me. So I'm principal expert developer in T-Systems with more than 10 years experience, mainly in bloody Java Enterprise. Yes, and although I come to you from Russia, from St. Petersburg, I'm a co-lead of a Bulgarian Java user group. So that's a long story, but still I'm quite involved in this Java user group. I'm a conference co-org. You can follow me on this Twitter. And as you see, I'm not only programming. I really like flying airplanes. This one I have the honor only to reprogram, not fly. Okay, so plan for today. So we will try to rethink the way that we use our resources in our system. So the main goal is to achieve this. But before doing this, let's try to understand the word asynchronous as it is. Lower. Oh, put it like this. Whoa. Whoa. 1, 1, 2. Okay, great. So the main idea is I'm going to achieve it by understanding or trying to understand the word asynchronous. So what is asynchronous? This thing I got it from Wikipedia. So I just read it. From a computer-controlled timing protocol in which specific operation begins after receiving a signal. So, and the operation as they go, they're not going the same rate or exactly the same rate like something else. So in simple words, we want just to start the task of doing something somewhere else. As it is, please let me be notified that this process is over, and I'll try to handle the result as it is. Or in terms of Java, it will be a little bit complicated. We'll just start a new thread, do something there, and try to extract the result with a very much effort, as you know. And why should we ever do this? Why? Because it can be fast. It can be faster. And why can it be faster? Because it's not going to be blocking. It's going to be non-blocking. And why? Because there will be no gaps between the tasks. So blocking is evil. Blocking is waiting. It's doing nothing. So we should try to avoid it in all cases. So, and to get the right understanding how to do it, we have to take a look from a different perspectives at how it happened. Because actually not only one technology, several technologies made it possible for us to have this wonderful approach in Java8. So let's first take a small evolution of the multithreading in Java that we say. So everybody from you believe, so how many? Everybody's coding Java? Somebody not coding Java? Why? Okay, so I think that as we're coding, so everybody has tried this construction. So we want to do something on a different thread. We just make a thread which implements runnable interface. We just implement the function run and we start the thread. The other option will be to extend the thread. Okay, it's wonderful when you start it, but when you try to extract the results, to wait for the threads to complete, to stop them, to yield them, and so on, it's really complicated. So with few examples it's good, but parallel programming is hard. It's very hard. So every time we try to do something in parallel, we are really disastrously hard. And to do this better, Brian Gotts 10 years ago wrote this wonderful book. How many of you have read it? How many have understood everything was written there from the first time? You're amazing. Yes, I still read it every year. It's not because it's a bad book, because it's an amazing book. It's my truly beloved book. But I think I'm not clever enough to understand everything from there, but I still have to implement all these things in my job, so I have to try different approaches. So, as we continue the exploration of the API, in 2004 in Java8, there was introduced some called concurrency API, which actually puts some kind of better handling or better understanding of what we have there in this multi-threaded world. So we have something called executor services, well, which we can use in different configurations and different ways. Our resources, we have had this idea of we can pass this part of work to this execution that pulls this executor services and get the work out of there. Still, it was hard, but with them actually came the future. Yes. And what is a future? Just in terms of computer science. In terms of computer science, so a future is a primitive for creating multi-threaded applications. And you will be quite surprised, but future as it is not something new. It's not something new. The first concept of future was actually introduced in 1977. It was way before I was born, by this wonderful gentleman like Henry Baker and Carl Hewitt in this paper. And let's actually explore what is a future. So, for example, we have a function. This function produces some work. So we need to do some work in order to produce some result. And what do? We put this work inside of a container. Container is not conceptually, described in this work, but containers are now everywhere. It's a new trend. So putting a word inside of a managed container is something that corresponds to the concept and the idea of the future. So we put it and we observe it and we care about it. This container actually cares about this work. And putting the work inside of a container as itself, it's called another thing. So it's called the promise. Promise and future always come together, as you probably have heard this word. So putting a work inside of a container conceptually is a promise. And you'll be quite surprised that it's not something new too. It actually appeared even earlier than the future itself. So it was 1976 when Daniel Friedman and David Weiss introduced this. And you see that Peter Hebert called this thing a little bit differently. He called it eventual. So just mind the core of this word eventual comes from the event. And what are the actually main concepts of futures? So the future, it observes the work which is happening there inside of the container, and as this work is done, we make callbacks. So the container tells somebody who will handle this result there that the result is okay or it's not okay yet. And there is another very important thing that is about the concept of the future, that transforming result. So inside of the container itself, but you don't have to. You are not allowed to leave the container. So all the transformations of the result are going to happen inside the container itself. And if you leave the container, so you are leaving this asynchronous world. So you're just, breaking the law. So conceptually, the main idea is that before actually getting the final result, this result should not leave the container itself. Let us have a look what is the future in Java. So you probably have seen the code like this. So you get from this concurrency API from 2004, from Java8. So you just get some work, submit the task, and what do you have to do? You first ask, is the work done? Is the work done? Is it done yet? It's not done yet. Or you just put this get, just give me the work. So the API itself is very, very simplistic. So we can ask if the work is done by isDone function. We can get the work, and we can even get with timeout of the work. But there is one small thing that we currently not realize by doing this. So these two methods, gets and get with timeout, are actually blocking. So, and here we are breaking the law. We're not allowed to do this because what's happening? If we take two threads and observe their work, you probably see that if we submit the work and then get, the main thread, as it pushes, as it calls the get method, is still waiting, is blocked by waiting the result of the other thread. So actually we have not actually done the work better in another thread. We actually have two threads, which is one is blocked and one is working. That's not good. That's not something that's gonna happen. We want to have something like this when the main thread actually, gets or calls the get method. So the other thread is working, and here in this gap, we want to do something more useful. And from the definition, as I told you, we don't have to wake a block. So how it is possible not to wake a block? We have to make callbacks. Yes, callbacks. I've made a very simplistic, wrapper to help us do this. It also done with some goodies from Java8, like suppliers and consumers and so on and so on. It's just a wrapper between the task, and we can use it, and it's nice. For example, we want to call asynchronous and calculate Fibonacci's numbers. So as you see, we get a single thread executor, multi-thread executor. We can pass whatever we want. We get the Fibonacci's numbers, we get the executors, and then we have the callback method, something which will be called after we get the results done. Or if we have some examples, we will print the stack trace. That's okay for now. You see, it's quite readable. It's beautiful, I would say. But when we have to make some chains of other objects there, for example, you first have to calculate the prime numbers, then you have to calculate the Fibonacci's numbers, and then you have to print, for example, an intersection of them. This code becomes unreadable and undebuggable. You see? Somebody have tried doing something like this? I see no, because it's ridiculous. Yes, because the real work is done actually here. I've painted in red. So we get the primes, we get the Fibonacci's. Yes, we just, here I even cheated. That was a good idea first to make the intersection asynchronously, and then after we done it, we have to print it. Now I do it synchronously because I don't have enough slide space to show all the code. Yes, so it's ugly. It's not a good way to do this. So, and probably the question is, did they do this somewhere else? Of course, it's in JavaScript and Node.js. So, as you know, as JavaScript actually has no threads in its language model, you cannot write threads with its expressions. So they made this wonderful Node.js stuff, which is based on non-blocking APIs and event-driven modal. And of course, everything there was callbacks. Somebody of you tried to use this? Well, I did it as well, and I thought that was so much cool, but in reality, after going to productions, we've got callbacks everywhere. Yes, and it was totally undebuggable, and we got to something which is called callback hell. Yes, it was, we lost more than 60% of our time just, fighting these structures. And as you know, the result is you say the word callback to JavaScript developer right now, he will start crying instantaneously. Yes, this is a wonderful phrase by Venkat Subramanian. So, in reality, it was not that much cool. Well, in reality, I mean in production. And in promises, another library called promises kind of fixed that. So instead of writing this stuff like, function inline and function inline, callbacks in function and so on and so on, with a small library called Q, we can achieve something very much readable. So we can just make chains of asynchronous calls by using then function, and we can even gracefully handle the exceptions, like with this catch function. So it was pretty nice. And this kind of, I think, saved the world of this enterprise development in JavaScript, because then you just, it will be just prep. So, and what actually happened in Java world? The first example, as I know it, is Listenable Future by Guava. So they have addressed the same issue by extending the functionality of Future. By adding these transformations inside of the container itself, and trying to make it with callbacks which are not blocking. So, but it was complicated, you know. Um, to make something really useful. By the way, Guava is used by Cassandra. Some of you use Cassandra as a database. Nobody, really. Okay. Well, there was the implementation of good implementation of a listenable future. I mean, so it was really good because databases bring latency. As they bring latency, it's this very good idea to return not the result, but a future of this result. And you know, the guys from Cassandra, they really understood that this will be a good option, and they've used this Guava library. And to make this, you see, you just have to make some extra steps by adding listenable declarators to the fix of to the executor, and you then have to do this listenable future. You can add callbacks, but you know, in Java 7, it was really complicated because you have to write all this anonymous classes to do this. Although it looks good, but it's just to function on success and on failure. But in production, it was horrible. Again, it was hard, really hard. And Guava also followed the idea that the futures, the result inside a future has to be transformed. So they have introduced this transform method. So the work inside of the container, I mean container in this conceptual word container, that does not have to leave this container to be fully asynchronous. So this actually gave us a wonderful opportunity to transform the values. So we were really close to, let us say, theory of futures themselves. Another option is JDeferred. I believe everybody have heard of Always Almirite libraries you cannot afford to miss. So it was also mentioned there. So JDeferred followed the same model with deferred promise library like they did in Q library, and it was inspired by jQuery and Android deferred objects, and it actually gave us the opportunity to create objects and make chains of this object by using them function, by completing by done, by gracefully handling the exceptions with fails, and so on and so on. So it's a wonderful library by Ray Tang. Actually, I had the honor to meet him, um, and this is a good option if you are not in Java 8 world, I believe. Although or you really enjoy doing this thing in the style of Android deferred objects. So it's a good option. Wonderful. This library is beautiful. But have you ever experienced this situation that you are not allowed to use some of the libraries in your code? Everybody? Yes. So you to introduce a library to your code, you just cannot do this. You're not allowed. How can we do this? Of course, because we have to switch to Java 8. Yes, because everything's inside and Java 7 is end of life. I've just talked to one of the colleague speakers. He said it's still in Java 7. How many of you are still in Java 7? I don't know. I'm not. I mean, not Java 7 as JVM. You're running your Java 7 code. Most of you run your code on Java 8, but still write everything in Java 7 using Java 7 JDK. If there's nobody like this, it's just amazing. It's wonderful. In 3 years, finally. So, and how do we do this in Java 8? So it's done only by one class. I personally believe that this class has to have this impact of change like the streams and the lambdas did, but it was kind of forgotten because lambdas and streams were so cool and everybody thinking them. But only one single class, which represent a fully different approach API, actually made a very big change. And this is only a class called CompletableFuture. So what is it? So it's in core library since Java 8. I was playing it with it even before March 2014 when I compiled my own JDK. Somebody have compiled their own JDKs? It's so fun, really. Amazing. And how it's done. So they've got this regular feature from, as we have it from Java 5, and they have extended the interface with another interface called completion stage. I probably believe that everybody knows that you can make multiple inheritance of interfaces in Java, not the classes. So they've just put another inheritance of interface, which is completion stage. And actually all the magic happens here, in this completion stage. So this completion stage allows us to make a wholly new world of approaches that we can use in our program. So in composition of elements, function resolutions, we can transform inside the values. We can complete them. We can make chains. We can make flows of tasks, and they are all available in async operations. Sorry about that. So, but before that, let us have a small foundation of actually what we have. So, because as I told you, several technologies made it possible. So, first thing is lambdas. In Java 7, as you see in Guava, mainly, so making this anonymous classes was horrible. It was undebuggable. It was better readable. Now you don't have to do this. So you just use lambda and method references. So, and another foundation, which is the biggest achievement, I believe, is the fork join. And since it's available from JDK7, it's really a perfect helper for us for CompletableFuture, because the algorithm itself is really good, and it's mainly good for creating new tasks. You can create. It's optimized for creating new tasks, and it cares very much for cache corruption. So if we take a look of our process and have several tasks in it, so the idea is that if we have the resource, we'll put everything in one thread, because if you put everything in one thread, so the caches will be filled with the information that you use most often, and you will really benefit from the idea that your data is already in the cache of this thread, of this processor. So you just facilitate it. But if your queue of one thread becomes full, and the other thread is doing nothing, there is something called like work stealing. So it just takes the tasks which are down there in the queue, and it steals the tasks, and it helps you to utilize the other processors that you have. So it's wonderful, and it's something I call a good combination of technologies that make it very easy and very handy to use the multi-threaded programming. So, and now if we're back to CompletableFuture, let's take a look at it. So, although the main idea of this talk is not to observe an API, but try to, I call it ThinkAsync. That means I want to force you to before getting a task ready, to try to facilitate other methods of modeling, just like done in this completable with this asynchronous approach with CompletableFuture. But still, let's have a look. So CompletableFuture, as I told you, is just a class. It's one single class. And how can we create it? So we can just create a class, just a new function with new, but it will do nothing. It's an empty container with nothing. There is some more handy methods. Like for example, you can use methods like supply async or run async. So supplier takes the supplier. It means that it takes some data, something that supplies you with the data, and do something with it. Or just run async. It means that when your task is ready, just run somewhere else asynchronously, a thread, something which does not have to return result. Yes, and if you see, there is another option here. You can pass in an executor, which makes it very powerful. So you can just, use just a supplier, or even have your own executor there and use it. But by default, ForJoin common pool is used by default. Here, I just want to say it again that ForJoin is cool. It has, it runs. If you start a JVM, you have this resource available, like ForJoin common pool. But not only you have it, all the JVM has it, so it can be polluted, as I say. So many other applications can use for a join pool, and this can be an issue of results. So if you care about, special conditions about executing your stuff somewhere else, you can pass in an executor and it's done gracefully, as you see. So another option is to complete the future. So you just can complete it. There's a function being complete, or you can complete exceptionally and telling you, okay, that something's gone wrong. You don't have to do this, and you can complete it only once, and that still actually does not exclude blocking. Just have this in mind. And the other option is to use the built-in methods that accept and then run something, and it will stop the chain of your actions. Just let us have a small look at it directly. So I've prepared some code for you. So we get prime numbers. So I prefer not to use something which is bound to internet, because unfortunately this is one of the first conferences when I have amazing internet for speakers. It's great. Thank you so much. But this example I use prime number because it's latent operation. So once again, latent, we'll come back to it, but these completable futures are perfect for latent operations. So what we do, we create a completable future, and we want to get primes. So we just call our method by method reference, and get the prime numbers. And as they are calculated somewhere there in our for join pool, we want to print them, and want to do nothing else, just to print them. And we call this terminal method that accept. And after it's done, so we get the system out and reference to, oops, not new, but print line. And it's okay. Look, we've made a small chain of events that happen asynchronously. And if we run it, let's see what's going to happen. So, oops, yes, I have to finish this line. Just give me a second. Yes. Let's run it. Oh, nothing happened. What's wrong? If we say, for example, it's a print line with Buongiorno Ticino. No, I think that was bad one. Buongiorno. Like this? Yes. Ticino. Yes, and run it again. What's gonna happen? Oh, where are our primes? Do you have any idea where our primes are? You do. Anybody else? No, they're actually happening. They're exactly not that calculated, but the problem is that our program runs faster than the calculation. And as you see, this apply, I think, the sync means that we're doing asynchronously. That's why we're starting a new thread. So, if we make some waiting here, like, for example, in readline, we will see, or just read. We will see that if we run this thing, we will have then Buongiorno Ticino, and then come our prime numbers, because they are latent, they're running a different thread. And now if I just press enter, we will stop the execution. As you see, it's wonderful. So we've just done a multi-threaded programming without even using the word thread here. Look how amazing it is. And if we have a look here in this calculation of prime number, we just print the thread actually that does here. Thread, then current thread, that get name. You will see that it will show us that this thread is a for join pull common thread worker 1. You see, without even doing all this ugly stuff with threads, new threads, starting, joining, and so on, we've just done multi-threaded programming from our code. And not multi-threading, even asynchronous, because we first got the prime numbers and then we actually printed them. This is amazing, you know, this is truly beautiful. I really like this approach. Multi-threaded programming without the word thread, because I'm bad at multi-threaded programming. And do you remember this? That actually all the transformation have to happen inside of a container. We cannot pull out the value and put it somewhere else. And then we have this wonderful option, then apply. So we can transform the values just right inside of the container. So I'll just make a small demo. We'll use the same stuff, and here in the middle, as we got the prime numbers, we can, for example, I've prepared a small transformation, then apply. We can use then apply, and transform this calculation by using, I have a function that actually calculates the average. It takes the list of something and gets the averages. And if we print it out, so we first calculate the prime numbers in our asynchronous thread. Then we transform this value in something else, like for example getting average of it. And after it's done, it's printed. We don't have to care about all these synchronizations, waiting, yielding, and so on and so on. So that's, for example, for me, that's magic. I'm totally in love with this. So, as I told you, by then apply or then apply sync. Here, as you probably saw, I use this async. So if we use then apply without async word, we're going to do it in the same thread. If we use async, it will do it in some other thread of the executor. So, wonderful. As I told you, just in one single line, for me it was a single line, we can make massive asynchronous calculations, and it's beautiful, it's understandable, it's readable. You don't have to care about this. So if we dive a little bit more deeper, we can transform the way the objects inside of all this chain that we formed from the events in a smart way. So there is another API function called ThinkCompose, or ThinkCompose async, and it's done for you to avoid something like CompletableFuture inside CompletableFuture, because CompletableFuture is just a class. You can put CompletableFuture inside a CompletableFuture, and it becomes strange. But if, for example, our calculations, it works like just a flat pipe actually. If, for example, our calculations like this asynchronous reading of file returns us a future, we can then, with compose async, just give it this future, and it will unwrap it for us, get the result, transform it in some way, process the content as it's written here, return us another future, and then we'll accept it and print it. So by composing, we can make a good flat map of different completable futures, and it will all go like a flow. Yes, we don't have to dive inside or get out of there. It just goes as one flow. It looks beautiful. Or we can even combine and reduce. For example, we have to have several steps that actually form the next steps, and we can then use the API method called then combine, and we can do it in a single thread or a different thread. If we take a look at this function, for example, we have first to calculate primes, then to calculate Fibonacci's, and then to get intersection. With just futures, it will look like this, you know. So we get primes, we get futures, and we have to intersect it, and it's really not beautiful like this. We have to wait. Somebody have to wait for that. By the CompletableFuture then combine, we can do this easily. So, or we can don't want to make a further processing. We can just accept both of them and just print something else, or run something after both. And we have other options, like for example, I want a first available result. It's a good example here is a DNS. For example, you have several DNS servers, and you say, okay, people who knows that address, and the he asks all of the DNS service, and they say the first comes, okay, I know this address, and we don't really care what the other will say. We just use the first address, so you can either accept either method or run after either method. So one is consuming something, one just runs something. But if we want just the first available result, what happens actually to the second result? Here's a good question. Because the second result, actually this future that has the second result is not closed or is not disappear. It just, stands there. So handle with care all this thing. Or you can even get the number of dependents, because one future can have many dependents. So you can apply to either, you can even have the option to pass many futures and to complete all of them or any of them with the methods in this API, but have a look at the results, not results but return times. So return times of all of is void. We cannot predict what is the future actually will gonna be. It's gonna be object, integer, or void or something else. So void is the only option here, or any of the other thing is option, object. So it's hard. So these functions are rarely used. I never used it in my life. So exceptions, we can handle them very good. So we can complete exceptionally or handle something gracefully. So the exception is propagated down to all the chain of the events that you have. So handling options here, and you can use it. So for example, if you have x value, which is good, you just go ahead. Or if you have a problem, so you just print it. So we get a lambda with the function. One is value and one is exception. So if we read the file as in the previous example, like apply sync, then compose, process it, then accept the results. And if something happens somewhere in the middle, unlike that example that I gave you with asynchronous, we print handle the exception all the way down to the call. We just call exception in print and trace. So as you probably noticed, the API is really big. It mostly fits all this pattern, but it has almost 60 methods inside. And as I talked to one of my colleagues, why don't you use CompletableFuture? They said because we are scared. There's so many methods inside. We just, just if you see and we're scared, it's not good. And still, if you overcome the scare of it, and you can organize your work in flows. So if you do this, then that, then do this or that, or the failure, please recover. If you start thinking in workflows, events, and tasks, so for example, you get this this representation of data. So CompletableFuture exactly for you. You can do parallel stuff without even thinking about being parallel, because you organize your work in flows and events and tasks. Everything will be handled for yourself. But as I told you, we have some bad heredity, and it's called the get function, because we're still inheriting the get methods from the future interface, and it's blocking. And it's really bad. But there's another option called join. So join is something like get function, but it does not throw you checked exception. There's a good example of how to use this. For example, we have an application which does have some. Can you read it from the back? Is okay? It's readable. So it's not readable. Okay, I'm gonna make it bigger. So there is something like sending an email. It's artificial. So threads sends an email just in one second. He needs to get the thread done, and it's just a piece of work. And how can we do this? So if we are thinking in terms of fire and forget, we can do a parallel stream and send the emails to somewhere else. But we can do it a little bit different. So we can make a completable futures of sending of these emails. Just send this email. I said do useless work. Collect them in a future result, and then we actually have to join the results. And let's see how this may work in terms of using the completable futures. So if you have the result here, here is printed. I'll do it a little bit more. So if we use parallel streams, you will need about 2 seconds to run this because parallel stream use the for join common pool and you cannot use other pools there. You're not allowed by the API. And the completable futures where we pass other execution services, you see the same job took us only 1 second and 9 milliseconds. So have in mind, you have this wonderful instrument of defining your own execution pools and do again with streams parallel jobs here, and this runs really faster because there you don't have the control, here you have the control. And it's a perfect idea of a fire and forget principle. So you just need to send the emails, just do it in parallel, do it in the completable future, fire them and forget. It will happen somewhere there in the background. You don't have to care about it. Okay. So, but get is still there. Another option is just to obtrude the value as it is, but get is not a good idea. So, for example, you have a service, which is a REST service, and you have to calculate some values and you have to return it. One of the options will be just to make completable futures and to calculate everything, make the intersections, but then you have to return something. You still have to make the get function at some point because you have to return string. And you see what's happening inside is that you have something that's calculated prime, something that's calculated Fibonacci, but the main function is still waiting there. So, and if you take a look of what's actually your libraries provide you, like this is a good example that we have used in our code, is that down full of the path of the technologies that we use, we can even render this result asynchronously. And it's very good because here we return the completable future and we get this asynchronous response, and as we print it out it all goes asynchronously. So actually the execution of this thing comes like this. We have a lot of resources, like first we get just fires the events that are going to happen, and only after these events are our tasks are calculated in a good way and they are ready, only then actually this result is printed. And if we have a look, I even have made some services for you. I believe that Tommy is still running. As you probably know that yes, it's here. Calculation of this is a REST service which is fully asynchronous. That all of the chain we get from calculation to all of its part to asynchronous response rendering, you've got this result fully asynchronous. So that actually is a good plus and a good drawback of asynchronous execution is that you cannot make stuff synchronous here and asynchronous there. All of the chain has to be asynchronously done. If you break the chain, you're breaking the law of the transformation that has to be done of the containers. So think about it. You cannot do this here like this and here asynchronously and then combine it together. If you do this, you will block somewhere and you will lose your resource. So this is a big power and still drawback. So it's very fragile. So as you see, this is done fully asynchronous. So we have the instruments to do all this thing asynchronously, like in REST service. This is something that we've done in our job. We have a very small microservice which has done a very latent search, and this latent search actually gave us this this way we saved some resources by doing latent search by providing the completable futures to them. Just remember, get is evil. So if you have get in your code, that's bad. So just a few words about Java8 that comes this July, maybe. I don't know. So there are several JEPs in it. I will just scroll through them. So one is that as you see, we can do some default completion of a future. So as one result is calculated, we can complete the result, and as it's not yet done, if we get the get method that's become not blocking, it gets the default result and then returns you the real result when it's calculated. I personally find it not good because there you cannot predict what will happen, what will be the predicted result. So, but still, this job is alive. It's strange. I don't like it. The same as for is done. And the other good thing is here are the timeouts. So you have timeouts in your code. So you get the possibility to make if you have operations that are really requiring some time to be completed, but not more than something like specified, you can do the timeout, and then you have the possibility to or give result or give an error. So that's a good option. The other idea is that you can complete it on time. So please explore this job. This is interesting. And just to say a few words, so this actually it comes from the idea that this way of programming and this thing of doing approaching the tasks that you have, it looks like very reactive. So as I say, reactive once again was the new cloud. So if you do reactive programming, you're a really superstar. Yes. But until actually serverless came out, serverless is now stealing more people on conferences on that talks. But it's actually not something much new as well, so it's just an observable pattern. So, and as you see, the keyword asynchronous here, and the Java8 here supports this way very good, really nicely. So, as everything has its manifestos right now, Reactive has its own manifesto, I probably read it. So, this idea of responsive, elastic, resilient, message-driven, more like message-driven event, really fits well to Java8 CompletableFuture's approach. So you have responsive, so you can scale your application. You're resilient, you handle your errors gracefully or exceptions gracefully. Elastic. So responsive, I mean in terms so you can control the response, you can control timing of it. So it's quite reactive. And as I told you, this approach really optimizes your CPU usage, your cache failures, and so on and so on. And in reality, we came to one of these graphs. The blue lines actually is the CompletableFuture implementation of the service that we made with it, which was fully asynchronous. And we see that during the day we can receive more responses for our job, just because this timing between switching the threads and switching the tasks, there is no waiting, there's no blocking, so everything happens just right after another, and there are no possibilities for one thread to be waiting for someone and be blocked for something without, because we are fully asynchronous in this approach. So as you see, it looks really nice. It fits very nice the reactive pattern. The good thing, it comes out of the box. You see, when it comes out of the box, it means that it's tested. Something that people forget. It means that it works as it should work. If you use third-party libraries, something may break, and you don't have control of it. Here it comes with a JDK, so it's tested, it's working, and just handle it with care. And once again, as you write the application there, and you have some idea of switching from one task to another, just mind the gap. An asynchronous approach gives you the possibility to exclude this, theoretically, exclude this gap from it, from doing your stuff. And that's probably all from my side. So, grazie mille, vielen Dank, merci beaucoup, thank you very much. So for the questions, I'll be available there in the auditory. And one small word. Alvarez Almirait wrote some nice examples where he used completable futures, and so please check the links that I put in the end of the presentation. It will be available on the site, I guess. I will publish it. So thank you for your attention. Grazie mille. Okay.